first session that we have on the second day of Inércia. And we have a very special session sponsored or cooperated with the LOAD ZX Museum, our longtime partner. And to explain the project a little bit, please come on stage, João Diogo Ramos. So if you want to introduce, please go ahead.
Yeah, good morning, everyone. I think the main thing is to introduce Hugo, which I'll do very briefly. Over the last 2 years, this was an endeavor that became the most important project we ever did in the LOAD ZX Museum, until now, because we hope the next one will be even bigger. And as we will see, it's a very special project for us because it was very important for the work done in this area in Timex. But I'll leave all of that for Hugo to explain. What I would like to stress is that for me, as co-founder of the museum, this is a very special project because it's the first time we had a team from the museum not working individually, but working together, complementing each other to put their skills at the service of recovering something that was lost, and it is very important for the Portuguese engineering. But to know more about that, my good friend Hugo Pinto, who will be the one presenting all of this, is the project leader, and thank you.
Thank you. Okay, so first of all, thank you, João. Thank you, Philip. My goal for today is to spend, I believe, the next 15 minutes, let's see how that goes, in explaining a little bit of what this restoration project meant for us. And I pretty much have it divided in 3 main points. One, I'll tell you the story behind it, because it's, from at least from my standpoint, a fantastic story. Then we're in a tech event, right? So I'll go deep and go to the inner workings of the stuff to tell you a little bit on how does TENET work, how does the network works, what makes it tick, and then I have something here on stage that we'll be sharing and that everybody can test out, and the folks at home can then see working, so that we don't do just slides, basically. So that's my plan for today. So. First of all, a bit of a brief notice regarding the whys and whereabouts, right? So why is this so important? Why is hardware preservation so important for us? Well, things decay, right? This is 35, 40-year-old stuff, and capacitors, resistors, whatever, this stuff goes bad. And as it goes bad, we lose the capacity to boot up and to experience these machines that are not only part of our nostalgia for many of us, but also they are an important part of computing history. So there's a goal, and there's a noble goal, not just the nostalgia thrill, right? But there's a noble goal in actually doing hardware restoration and preservation for these machines. They are part of what made the machines that we use today, those machines, right? So most of this stuff is usually rather commonplace, and most of this stuff is usually off the shelf. Still today, just a few months ago, the Z80, the processor for most of this stuff in front of me, stopped being produced 40-something years after its initial production date, which is crazy. So for many of these components, we get them off the shelf still. Nonetheless, there are some which are specific for that specific architecture or that machine, and in those, we do face a challenge, which is if they were limited production runs or just made for that specific instance, we sometimes find ourselves scavenging for machines, trying to get alternate components to replace those. And that sucks, because we are diminishing the available machines to actually go through, and we are losing. It's an ever-losing game, right? Because the amount of the available machines gets fewer and fewer and fewer. So trying to replicate and trying to be able to go deep and rebuild all of those tiny pieces, for us it's really important. And specifically for an 8-bit museum like the LOAD ZX, which gathers and caters to both ZX Spectrum machines and Timex machines, we take very, very cautious notion of what the inventory for these unique pieces we can try to preserve. And one of those was something which is in the heart of most of the Timex computers. I'll discuss one of the differences between these computers in a bit, but one ZX Spectrum clone, which is very dear to our heart, is the Timex computer 2048 or 2068, depending on the model you got. And one of these pieces, that one over there, it's pretty much the heart of the system. It's what makes it tick. It's the orchestrator. It's what pretty much says to the CPU, look, you now can fetch a little bit of memory. Then you can just produce a tiny bit of computation. Let me just refresh the RAMs here, and then you can do a little bit of computation more, and then you can eventually read a bit from tape, and it all goes round and round and round in a very fast orchestration that this little piece is responsible for. And it's a limited run. It was produced for these machines and never produced again. The Spectrum has a very similar chip. It's called the ULA, the Uncommitted Logic Array. But this one has been reverse engineered quite a while ago, and so we can rebuild it. Nonetheless, that work hadn't been done for the SCLD, the ULA of the Timex computers, if you want to think about it that way. So that was actually our first project. That's where the museum started doing hardware restoration. And thanks to this guy here, to whom I must give credit for, because it's really due, Alvar Lopes, he pretty much did a test-driven approach to the whole endeavor. He went every use case per use case, every signal that the SCLD had to emit, and he tested it one by one in a simulation set of hardware, which is part of what he has in his hands over there. And we produced a synthetic VHDL equivalent of the SCLD, which was then synthesized in a modern chip in such a way that we can now produce SCLDs like this one, and at least that part of the Timex computer, even if it dies on us, we can still replace it. So pretty much the whole thing that you see there on this slide can now be absolutely reproduced from scratch, and we can build our own Timex 2048 computers and 2068 computers, basically, because all of the other stuff is pretty much off the shelf. So that was our first hardware restoration project, and it was presented by the museum's team and Alvaro himself on a very special event to my heart, which was the 40 years celebration for the ZX Spectrum. And in this specific event, there was one session dedicated to Timex computers, and specifically to one branch of Timex computers, which is Timex Portugal Limited, which was actually very nearby where we're doing Inércia right now, in Caparica, a few kilometers from here. And in this presentation, two old-timers, they're old-timers by biological age, but really techies and hardcore enthusiasts like us were on the stage presenting their stories about what those years meant to them, and presenting some stories on the projects they did. I was on the audience, and the funny thing is that I was not expecting a very technical talk. So the talk went a bit deeper than expected, and they mentioned couple projects that were on the production line for Timex computer back in 86, 87, it would depend on the projects. And one thing I found interesting is that these were projects that they had huge potential, but they never made it to the market because the company was already in financial dire, and the whole thing was just their last push to try to make something that would work and to make something that would make quick money so that they could eventually pivot off to some more profitable endeavor. And one of these projects was absolutely amazing, was this idea for a specific business opportunity they had in China that was being explored back then. They had this thing which was a network, a computer network using 8-bit computers for the classroom, in such a way that you'd get a teacher on his teaching desk, and up to 24 stations, a full classroom with 8-bit computers that would orchestrate between one another, fully transparently to the 8-bit computers themselves, and the whole thing was speedy, and you could load stuff, and the whole story was amazing. And it was also a very heartening story in the fact that they were doing it in overtime, and they were building small miracles from very few resources. I was there actually. I was out of frame, and I was amazed. And that moment, actually, something ignited there, which was this concept of crap. We need to make this happen again. We need to take whatever we can from the few artifacts that the museum has and make this happen. And that's where actually this story for today started. So there were actually two products, these lost products at Timex Portugal Limited. One of them is this computer network, and the other one was a computer model that never made it to the market as well. That's a hint for a future thing, right? But today we'll be focusing on the network. So what we were aiming at was basically, we had a few artifacts. We had one board, one large board, which was under one of these small computers that I have right here, the 2048. And we had an even smaller board, one of those that would connect to the edge connector, to the expansion bus of the ZX Spectrum. So we wanted to basically document the whole thing, photograph it, document it, try to reverse engineer it, and try to figure out what we could do with it, because the goal was putting it to work, right? So we had these two boards, as I mentioned. Looking at those, not being too technical, I know we are at a tech event, but this is 40 years tech, so I'm aware that not everybody might not be everybody's cup of tea. Nonetheless, we had two boards. One, which was basically a daughter board, a full board for one of these computers that would sit underneath the motherboard with an 8051, 8031 microprocessor and a set of circuitry around it, and a smaller board, the one with the expansion bus that I was mentioning, with just the 8031 and much less circuitry, but a gate array chip, like an FPGA these days, right? And actually, that's where the GA comes from. But they were similar in nature. They had the same interfaces. They had pretty much the same kind of circuitry that would make them kind of the same, one the evolution of the other, most probably. Here they are. So this is the daughter board, the big one. So we had stuff here. We had two EPROMs, one here, one here. We had the CPU, an extra CPU, which was the 8051. It's an Intel chip. We had some circuitry for line drivers for communication, and we had we had a memory here, a bit of RAM, 2K RAM, and we had these dip switches. That's all we knew. Plus, we had these two mystery chips, which are two PAL chips. It's programmable array logic, which is kind of, you can put many of those 74 chips, which are NOR and 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 OR gates. You can put lots of that stuff already compiled onto one of those and make it a black box in such a way that it carries the logic in, but with much less board space, much less real estate. So that was the first board. We photographed it back and forth. And we had the smaller one, which was also with the CPU, the Intel 8031 in this case, also the RAM, an EPROM as well, and this mystery chip here, which was a gate array. There's plenty of logic there, kind of like an FPGA these days. Also back and forth. Do bear in mind, for those that will be watching the video afterwards or in here, the amount of artisanship in doing some of those solder joints back and forth. So all of these are shunted back and forth. This is almost prototypable. So we had the boards, and we had a series of challenges. We knew we wanted to take the software out. We knew we wanted to try to reverse those black box chips that we had there, those PALs, because there was logic there that we needed to try to figure out how to get. And we wanted to get the system running, right? We wanted to boot up the thing. But this is a museum, so we also didn't want to do this in such a way that it would hinder the system, the only prototype we had, because our main goal is preservation, and only afterwards the restoration and the recreation of stuff, right? So that was our baby. We didn't want to hurt it, right? So we went through a series of steps. I won't delve too much into it because my main goal here is to tell you a little bit on how that works. But we pretty much took all of those chips to the two little black boxes that I was mentioning, the PAL chips, and we used the brute force approach. So we basically took all inputs for all of the chips. We had mapped the circuitry, so we knew what was going in and what was going out. We calculated all of the entry points and all of the combinations for entries and outputs, and we injected all entries, brute forcing it, and carrying out and saving the outputs. And then we did a huge logic reduction calculation in such a way that we took all of the bits that entered, we remashed it into logic formulae, and apart from that, we actually, if you guys love hardware logic programming, not everybody's cup of tea again, we basically recalculated the formulas that were there for each of the ships. One that was, which was dedicated to disk drives, and the other one which was dedicated to network communication. So we'll go through those. We also extracted the ROMs, so we basically copied the ROMs. We were very lucky that out of the four ROMs, we only got one bad. Unfortunately, it's the most recent one, that's 21st April 1987, and the other ones we ended up finding out were from 86, but they were all functional. So we could get the code from this, and we disassembled it. We disassembled the code both for the 8051 and the Z80, and on the Z80 we actually found nice signatures for the original programmers. Antonio Nóbrega right there, leaving his mark, which is actually on a fun note, the same programmer for a very well-known Timex word processor, TimeWord, which is basically also featuring his signature on the ROM code. He really did love to put his mark on. But this was supposed to be a network, right? And a network for classrooms, and classrooms required the educational materials. And we didn't have any of these software originally when we started the endeavor. But we ended up, the museum fortunately has a series of events and has a great outreach with the old Timex employee community. So we eventually reached out in one of these events and I got the mic on and requested, look, if everybody, any of you might remember that you might have a TENET disc somewhere, or something that says TENET, just please bring it along because we're doing this effort of trying to reproduce the whole thing. And fortunately, they came about, not only on that specific event in which one guy had some discs with the teacher's software, but we also got a series of discs. And this has stuff like geography, human body knowledge, plants, chemistry, stuff like, well, you would expect to use on a classroom, and we pretty much, out of a stroke of luck, got access to, we believe, the whole set of software that was produced for that classroom. So we were pretty much on a good line, on a good path to actually try to reproduce the system. So we knew, okay, let's do the hard work. We recreated the whole system and the whole logic diagram for the whole thing. From this, we actually did both at the same time. We were recreating the logical diagram at the same time that we were retracing the whole board. There was another volunteer here, which is not with me on stage today, Paulo Silva, and together with Alvaro, both of them, they retraced the board, and we got to do our own design. So we recreated the original board, the one that we had under the 2048, and we ended up creating our own system. So we created something. This means that we were, with physical artifacts apart, we were almost on the finish line. But nobody had an idea on how this worked, because we just had the artifacts, right? We had the ROMs, we had the PALs decoded, we had the ships, we could put ships on a board, but now how does that work? We actually tried to boot it, and we did boot it with various degrees of success, but at the same time, we were exploring the inner workings. So just before we go to a bit more discussion on how this works, I would love now to tell you a little bit of how the whole thing works. So we told you the story, but now what makes it tick? We are now in 1985, 1984, depending on the access you had to these things. And there's Timex and there's Sinclair. Sinclair was doing this very successful computer called the ZX Spectrum, which everybody on the audience and many folks at home might know. And Timex was doing a series of computers, mostly for the American market, under the brand Timex Sinclair. They were not especially successful on the American market because the American market was by then mostly driven by Commodore machines. So, and people would rather, for those that were not Commodore machines specifically, the experience was much more cartridge-wise and instant software-wise, so people would not have the kind of patience you'd get for the ZX Spectrum to load a tape with a game or some educational software for 3 to 5 minutes at a tape. So there was some pressure in, one, trying to figure out solutions to actually address these concerns, the fast loading and the degree in which integration with larger mass storage mediums would be needed, and also the fact that that specific market was not being addressed very successfully. So let's go a little bit on, with that in mind, let's go a little bit into what these machines are and how they address some of these concerns. So first of all, there's the Spectrum, right? Everybody knows the ZX Spectrum. If you don't know the ZX Spectrum, I have one here. It's this tiny piece of machine. It's, so, you know, funny thing, on conferences and on shows these days, we do quite a bit of those, and most teenagers go around and look at it and they say, look, it's a keyboard. It's not the keyboard. It's the keyboard plus the computer. You just need to connect it to the screen, to the TV that we had back then, right? But this is an 8-bit computer, tiny by today's standards, but still very large at the same time by today's standards. And this would run on a Z80 processor, about to 3.5 megahertz. And it features, that's the important part, a 16-bit address space. So it goes from 0 to 64K without paging, without any kind of trickery. And it can address basically 48K of RAM and 16K of ROM. And it's pretty much laid out like I have on the screen. So the first 16K is the system ROM. It's the software that comes with the machine, the basic interpreter, I/O routines and stuff like that. And the remainder, it's RAM. The first case of RAM right there immediately after the ROM, it's the screen, but that's not important for us today. But apart from that, it's a very basic machine with no specific coprocessors. So no specific video display processor, no specific sound chip. The CPU does the whole thing. So trying to connect this kind of computer on a 24-computer network would naturally present some challenges because it was already a very limited machine by the moment in which this was on the market. Actually, Sinclair's own edge was precisely in the fact that they would naturally mix not cutting-edge technology stuff that was not the very latest, but put together in a very economical, very smart way, right? At the same time, Timex was doing their own series of computers. So one of the computers they were doing were clones and versions of their own Sinclair-compatible computers for the American market, as I was mentioning. This originally started in Dundee, Scotland, and then, as the production was growing, was offloaded to a factory very nearby here in Caparica that had already been manufacturing watches prior to the Carnation Revolution here in Portugal, and that was pretty dormant. They had minimal staff going through the plant, but due to the offloading for Dundee, they eventually got to restart the plant, and they started building computers very nearby to where we are. And originally, they were building computers for the American market. But as the American market starting to wind down and Timex started to de-invest in the American market, the national facility here in Portugal, Timex Portugal, or TMX as I'll be calling it from here, this point forward, they started doing on a slightly different brand. So originally they were Timex Sinclair. These are Timex Computer. Just, if you look there, a tiny little bit of a different change in the branding. So they started to do their own versions of the original larger computer that I don't have here, which has a cartridge slot. And then after this 2048, which is the computers that we have actually here on stage, which is pretty much, if you want to think about it, almost a ZX Spectrum clone with some extra stuff. So for example, it has that specific chip that we reconstructed that allows it to have extra resolution screens and extra capacities for showcasing information on 64 columns in the screen. And it allows a series of changes for commodity. It has a nice space bar, which I personally love, and an output directly to the to a composite monitor, which makes it great for demos these days. So, and it features, of course, the CLD, as I was mentioning. Additionally, the market was changing. So Timex, as I was mentioning, and Timex Portugal especially, was trying to address the fact that people were demanding mass storage. And people were demanding something else than the tape loading mechanisms for their 8-bit computers. And funnily enough, this was something that came out of engineering effort from the Portuguese plant, and a small group of engineers, they started, many of those fresh out of university, they're starting developing their own ideas on doing products specifically within the plant, and doing their own products, not necessarily just manufacturing and assembling stuff for Sinclair or the original Timex computers, but doing their own stuff. And in late, I believe this started during early 1985, and it took pretty much all of 1985 to build, and the first product they created was this, which I have on the slide, the Timex floppy disk system, or FDD. And it's a funny thing. It's composed of a controller, which is this guy here in the middle. It's composed of a power supply where the energy comes from, and then 1 or 2 or 3 or 4, up to 4 floppy drives. And they use this hideous format, which is the 3-inch floppy, instead of the 3.5-inch, which we all know from the save icon these days, right? But due to logistics and the fact that they had an amazing deal for a bunch of these guys, they ended up using this to support their floppy disk system, and it's pretty much what's there. And this was actually the genesis also for the network. And it came out to be a coincidence of events that led to this. So that's why I brought it here. Why? Well, what's it supposed to do? First of all, it's compatible with ZX Spectrums and Timexes. So you can connect this to a normal Spectrum and it would still work, or you connect it to a Timex machine and it still work. And they made a very interesting choice. They wanted to make it transparent to the user. So you'd connect it to the machine and you wouldn't have any special software. You'd just use specially designed basic commands to address the disk. But if you had it connected and would use your computer just like normal, you would not notice the difference. But you could do some magic on the basic interpreter with some special commands, and you would load software from disk, save software from disk, and even communicate via a special serial port, because that controller had some serial interfaces that would allow you, for example, to connect to a printer, like the one we have here. And it was very flexible, actually. The way in which the controller was designed, this would allow you to connect 1, 2, 3, or 4 drives, and they could be any kind of, on the date, contemporary drives, so running from a 164K single-sided drive, which was the norm, to up to a 64K double-sided, double-density drive, which was really, really cool. So the whole thing was actually very flexible. And the way they did all of this trickery was actually something that came out of a bit of an unexpected place. They were wanting to try to create some way of doing this transparently as basic extensions. And there was another product on the market, which is this. I don't know if you guys know what this is, but this is an interface for the ZX Spectrum. Originally, most of this stuff was supposed to be in this stuff, and the ROM should be in this stuff, but Sinclair was really pushing this to the market rather fast. So this would allow you to connect and expand your ZX Spectrum with lots of stuff, with an interface on the side that would connect to a disk drive as well, to a micro drive, they call it. It's some kind of a special tape disk. They're tiny tapes, very prone to error. Everybody hates them. But the funny thing is that this also would expand the BASIC. And it would expand the BASIC due to some very, very clever trickery, in which, if you know these 2 books, plus the Bible for ZX Spectrum hackers, which was the complete Spectrum ROM disassembly, which most of the stuff here allows. Basically, the whole book has the disassembly for the ZX Spectrum, and the usual ZX Spectrum hacker would have this on their bookshelf. So it's expected that they would have not only this at Timex, but the description on how the microdrive system for the ZX Spectrum would work. And there's a funny thing if you were contemporary to these moments and do any kind of ZX Spectrum programming. If you write something stupid in BASIC, there's an error. But the way the error is produced is that the interpreter would go to a very special place in ROM, would go to address 8 via an instruction called reset 8 or RST8. And this would actually jump to 0008. And from that point onwards, there are some, it's 8 multiplied by 8, if I'm not wrong. It's a vector. And it would, then you'd have some instructions that would allow you to interpret the error in BASIC and then jump to the correct moment and jump to the correct message that should be outputted to the user. Now, what these guys did was something very simple. There's circuitry inside this that catches on the bus whether the CPU is running at a specific address or the CPU is jumping to a specific address on the address space. And if on the circuitry they detect that it's doing an RST8 and jumping to that specific service routine, it immediately switches out the address space and the ROMs and switches the computer to another ROM, which is in here. And that was the click, the haha moment for everybody. So the moment they do this, they switch the ROM to a new ROM with new routines here. And these routines, if I do something stupid in BASIC, like an instruction that should not be happening, I can now get an error handler, not on the computer, but on the on the new ROM. And I can now treat this error like if it was not an error. I can actually interpret it and add an instruction to write to one microdrive, or add an instruction to expand something that didn't exist there, or even add an instruction to connect to a serial interface that we had here. So this idea enabled these many other expansions for the ZX Spectrum, in which you'd be able to add new stuff, or to expand the BASIC, or to add new capabilities to the computer out of the box just by putting something on the expansion. And these guys at Timex, they ended up thinking, okay, if the guys at Sinclair can do it, we can do it as well. So they pretty much did the same. They created something which had extra commands. So in Timex operating system, which is the operating system used within the disk systems, you get new commands. Instead of cat, you'd get cat asterisk, which is invalid in BASIC, by the way. But since it's invalid in normal BASIC, it gets jumped to that routine, and from that routine, they have trickery that swaps the ROMs, and then they can manage it to list the directory. Or the save asterisk. The save asterisk is also invalid, but since it's invalid, it gets jumped to RST8, and then they interpret it, and they do a save onto the disk file. And for all of the instructions, there's 20, I believe, something along these lines. For all of the instructions that the new disk system BASIC would make, what they would do is that they would intercept it, they would interpret it, and then transparently return to BASIC like if nothing happened. This was extremely clever trickery that was done in basically this little box here, which is the little box that you would put onto the edge connector there, and that would connect to the disk system. And the way this would work is that this connects to the full-fledged ZX bus, and then there's this cable that would connect here, and this goes through a serial interface. So the Spectrum connects full bandwidth to the interface, and the interface connects via serial to the floppy disk system. There's a funny consequence to this. They were thinking that ideally, they could actually develop floppy disk systems not only for the ZX Spectrum, but for any other 8-bit computer that would allow one of these boxes specific to their architecture. And they actually did this. They did this for a French series of computers from Auric. The drive was called Jasmine. And it's actually a version of this that would connect to that other set of computers that had nothing to do with the ZX Spectrum, but would still work. Precisely because of the smart architecture in which they would mask the commands via serial interface to the controller, but still get a architecture-specific interface to the computer. Really cool, actually. And if you look at what's inside the box, actually, you can identify those components. So you get a bit of RAM, which acts as a buffer. You get the ROM, which acts as the shadow ROM, the one that has the routines to interpret the extra basic. And then you have paging logic here and here, which basically detects if you are on address for RST8 or on address 0 or on one of the exit addresses, I won't delve into that, then it pages in and out that RAM and does this instantaneously and very, very, very simple and transparent. So basically, this would allow everybody to connect to a ZX Spectrum. Actually, fun note, this chip here and this chip here are also some of those black boxes that I was mentioning before. They are PAL chips. So what makes a TENET? And how does this work internally after all? So we start with one of those tiny boxes with an FDD interface, the tiny box there, and all of the stuff that you'd find there to connect to an FDD system. By then, they had expanded this concept of the floppy disk system to a double floppy disk system. This double floppy disk system, which they called FDD 3000, very futuristic, would be basically like I have here, a system with 2 drives. Some would say, bad-mouthed, saying that this was an effort to actually sell more of these drives at the same time. Nonetheless, it was actually quite useful because it would allow you obviously to copy without having to swap back and forth. So we start with an FDD interface. Then we had a series of logic that would do the network. And we'll delve a little bit into this in such a way that you'd get a new CPU. We'll figure out why. A new CPU, an extra set of ROM for this CPU, and some kind of way to connect to other computers. And finally, we would add peripherals. So for example, in the case of the professor, of the teacher, you would add a printer specifically for the teacher in such a way that they would do the role of a print server, so that they would allow you to print, to have the students print stuff on the teacher's printer. Which is cool, because, well, we're talking about 1986, and this is a print server for 8-bit computers in 1986. Come on. So if we map this same logic that I had here to the board that we presented originally, the one that we had on the museum, and that we ended up reconstructing, what we had is pretty much the same components. So we have the ROM, the new processor, this RAM, which is also a 2K RAM used for information exchange, the paging logic, the shadow ROM, the ROM with the special commands, and a series of line drivers and level drivers for connecting with the network. So how do they connect? Well, first things first, they connect via an audio cable. I have one audio cable here. I believe one of my colleagues, João Encarnado, he was commenting that there was some other audio cable lying around. They connect via a very simple audio cable with a 2.5 millimeter jack, which you connect almost like token ring. So on one computer goes to the next, goes to the next, goes to the next, and they relay the physical connection between one another. It starts on the teacher, ends on whatever student you have, and you don't need to connect it back. It's just an open circuit. And they heavily rely on something called multiprocessor mode for the 8051 architecture, which is really, really cool. Why? Because basically, out of the text sheet, out of the application note, the tech sheet for the 8051, and also some 8-bit processors by then. This was not an Intel invention for the 8051, but it was actually quite popular for communications on the 8051's UART, the communication subsystem. You could do this. You could have an 8051 as a master and a series of slaves connected only by 2 wires, and they would orchestrate with one another using a very special type of data frame. They would put on an 11-bit data frame with a start bit, 8 data bits for a byte, an address bit, the stop bit, and the remainder would be idle traffic. How do these work? Whenever the master would want to communicate with someone, they would raise the address bit high, and they would put in the number of the slave they would want to communicate with. So this is a message for slave 1, for slave 2, for slave 3, whatever. And they would raise this bit. The other computers, they would be waiting for, on the line, they would be waiting for any kind of data package that would have the address bit high. And they would compare it internally to their own address. And if that's an okay, so if it's my address, they would raise their own signaling there and allow you to, from that point onwards, receive any extra bytes. If it was not their ID, if it was not their address, they would simply ignore all other bytes on the line up until the moment in which a new address bit would arrive. And so on this very simple communication protocol, you could have a master-slave system that would effectively connect on two loose wires to any number up to 255, because that's a byte, any number of slave computers. This is actually very similar to many communication systems with 2 wires these days. So on TENET, how does this work? This basically means that we have one master, which is the teacher, and we have up to 24 students. And they are here. They can be normal ZX Spectrums, they can be Timex computers, they can be anything which accepts the edge connector for the bus. And you have plenty of patterns that you can write here. So the most normal one is teacher-student. So stuff like the teacher would like to send a message or would like to send software to the student. It's purely master-slave. So the only thing the teacher needs to do, and on this machine, like the one we have here, we'll send out a package stating, look, here's a package for you to load. Here's a set of bytes. Put this in your memory. And the slave would just oblige. Would just take the package. There's some internals which are very, very deep, and that I don't have for this specific talk today, that would interpret this. They would store the byte in that RAM chip, and they would put it in memory. So first pattern is master tells students to do something, and they immediately execute it. Second pattern is the student wants to send out something for the master. But there's a trick, because as I mentioned, this is purely master-slave. So for this to be able to occur, the master needs to be polling, tac, 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 tac. The master is always polling the students, tac, 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 trying to ask for somebody else, look guys, do you have anything for me? Do you have any package for me? Do you have anything that you want to say to the network? And when this is enabled, then the students can send stuff for the teacher. So for example, stuff like, hey, I want to load a file from your disk drive. Or I can enable another kind of processing, which is having the students communicating with one another. So at the same time that the master is going, tac, 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 one of the students might say, look, I have a message for student number 3. Okay, give it to me. And then it's the master's job to take the message and then relay it to student number 3. The whole architecture is always, always, always master-slave. And this has consequences, so this has limitations, but it also makes things very, very simple, because you never have packet clashes. There is no packet collision because there's only one packet going through the network at the same time. And it works on 2-wire, which is cool, right? So also other consequence is the fact that things get laggy if you have many clients. That there's no coincidence in the fact that they found it acceptable to have up to 24 students. Why? Because after you do 24 polls, so check, 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 from 1 to 24 and back to 1, you lost quite a bit of time by then. And if you want an immediate response from one of the other students, you still have to wait for the next round of checks. So they kind of limited to the classroom, which was nice for the use case, but also very practical. It would not scale very well for a 200 client cluster, for example. Just before I show you what we have working, we actually are trying to do an extra bit of work. And the way in which we reproduce that main board, we are minimizing it. And for everybody that would want to try this out at home, the museum is making available in the near future not only the physical board in itself, but the schematics and the Gerber files and all of the stuff so that you can build your own extra Tenet or Tenet V2, which is a tiny version of this system that you would be able to connect to the edge connector on a ZX Spectrum and then toy around. You need 3 spectrums for this to be effective, but the moment you connect them and connect via the same interface, they are compatible with the real stuff. They are the real stuff. It's basically a re-implementation of the same board on a much smaller footprint, but still with EPROMs that you can take out that are not surface soldered, that you can take out, reprogram, and evolve the system. So, do you want to see this work? Let me try to do a small, woohoo! So let's do a small demo of it, okay? So what do I have here? I have a mini classroom. It's a teacher plus 2 students. They work side by side, so it's kind of bad for tests, but it still works for our demo purposes, right? So the teacher has connected a floppy disk system, an FDD 3000. Let me just swap drives here so that I can use a version of software that I'm familiar with. And so it has an FDD 3000 here, and a printer, and well, an 8x computer here. I'll just restart this and reset this computer, and you'll see that it starts to read the disk, and it pops up with a menu. Timex computer, please tell me the network size. They do this for efficiency. It could run with the full 24, but as we only have 2, it's much easier for that polling, right? And I get station 1, station 2, all are doing okay. Let me go. All are doing okay, right? And here we have the 2 student machines. Machine 1, machine 2. They are on their boot screens, completely normal. I can do stuff, very simple stuff with them, like, for example, 10, print, hello, Inércia, go to 10. Most used program in the history of the ZX Spectrum with some kind of variation. It's the programmer's hello world. I can do loops, run, and I can fill up the screen with hello Inércia right there, right? So, but this is a network, and I can do stuff with a network. So, for example, on the menu, I can do stuff like show the network status, which I did, show a pupil screen, load the pupil's computer with something, send messages, and stuff like that. So let me try to do something like that. So I'll send a message. This is pupil 1, that's pupil 2. Message. It asks me which pupil. I'll do 1. And I'll send a message. Hello, guys. And immediately, if you look at the screen, you could see popping out a message here. Actually, to disregard this message, the student needs to do OK, and it goes away. But I can do more stuff. I can actually show someone else's screen. So that's 2, right? So show pupil screen, 2. Aha, that's the screen over there. What are you guys doing, children? So I can pick on any student's computer and see what's happening over there. But I can do more. I can do, for example, I can load effective software to each of these students. So the same way I sent a message here, I can send software here. But not only software here, I can send software to both of them at the same time, to 20 of them at the same time. I can do a broadcast and broadcast messages, but also software. So let's do load instead of 1 or 2, I'll put 0, which is the broadcast address. And I'll do password .l, which is, look at the screen, they both resetted, look at the floppy, and it's running and booting up a word processor. This is serious stuff, I mean. So we're doing a classroom, right? Since we're doing a classroom, it's only fair that people learn how to use their word processor. And do bear in mind, this is 1986. Word processors were a novel thing on 8-bit computers. So that's really nice. But at the same time, I can, let's see, 2 computers. I can do a bit more fun stuff. So we can play a game. So after school, we can do stuff like load all of them. Pogo. And do bear in mind one thing, ZX Spectrum games on tape would take 3 to 5 minutes to load, right? We're not doing that here. This network runs at 33 Ks per second, which is 10 times the speed that a similar attempt using the interface 1 was using, which was 3 Ks at most. And well, while I was telling you this, the game loaded, and it's already running on both computers right there. But you know the funny thing they used for demos? And the guys at the mixing desk, if you don't mind then putting this on the audio screen, one of the things they did was actually to demo it running a novel piece of music, Mozart, right? So let's do that. Oh, the fidelity. So you could have them all both in symphony. I know it's not hi-fi. Nonetheless, it made for a beautiful demo with 24 computers running at the same time and playing the music at the same time. We have it on loudspeaker here, but they did not have the luxury of it, right? So, in recap, what did we have? Let me just reset them all because this is very nice for a demo, but it becomes annoying rather fast. So, we can reset all computers. 0. Bye-bye. So, they had pretty much made using, in this case, an extra computer that would offload, an extra processor that would offload the networking capabilities. They had created a system that would allow them to load software, send messages back and forth, and create a platform for both collaboration software and educational software to run on classrooms in 1986. This was done originally to address one business opportunity, which was on the Chinese railways, which was huge by then. So the Chinese railways had 10 million employees at the moment by then, and they were looking for a solution to actually address their classroom and their students for all of the employees for the Chinese railroads. And this was the salvation buoy. This was what would eventually turn around the Timex Portugal financial situation and make the whole thing good again. Unfortunately, it didn't turn out as well. They sent a commercial team to China. They spent 2 months in China doing demos every day. They actually were quite well received. They got an order or a pre-order for about $30 million, $30 million by then, which was huge. But the times had changed, and the opportunity was really tricky now, because Sinclair had sold to Amstrad, so they did not own, and they did not have the same relationship they had with Timex back then. And Amstrad was actually seeing Timex Portugal as kind of a, we want you guys to assemble stuff, not as much as a competitor for foreign markets. And the ROM that actually showcases that message was effectively copyrighted by Sinclair and owned by Amstrad back then. And there was no more air, no more oxygen within Timex to actually build a complete new ROM to actually take them out of the licensing problems they would have in shipping millions of these to China. So the project folded, and in 1986, beginning of 1987, we could have had a platform for 8-bit computers that would make education in schools, technical education in schools, dramatically cheaper than anything that would be able to be realized, what if until 15, probably 15, almost 20 years later on. So it was really a pity, but it's one of those stories in which good engineering not always comes to market in full force. Thank you so much for your time here. And after, if you have any questions, we can actually come here to the stage and test this out if you need be. Thank you guys so much. I'll repeat yours, no worries. Rui's question was, can we as a student hack the teacher and send the game for everybody else? Well, yes. The protocol itself is quite limited. Nonetheless, there's nothing that would stop the student to send a broadcast to zero. So, if you'd be creative, you could have a student that would have some kind of storage device somewhere or some kind of cleverly elaborated code and try to use it in such a way that would eventually try to broadcast it. Nonetheless, I do think that it's not as easy as it might show up, because the protocol for load code and the low-level routines for load code can only be executed on the teacher. You can spoof the address, all right, but then you have a problem, because the whole thing is, I will take one of these momentarily apart. Let me just, or at least put them forward to the other. Not even need to. I can scroll back on my slides. If you look at the board, there's this very conspicuous dip switch set there, and that actually states who is master and what's the ID for each student. So all of these computers are configured in such a way that if this first bit here is 1, you're the master. Otherwise, these next 5 bits tell you the student number. Now, on production machines, that we don't have here because we actually only have one full production machine in the museum, on production machines, they would have a plastic cover that would only make available the 5 bits that would allow you to set your student ID. And even this one should be, I would assume, covered for live students. If you were an ingenious student, you could actually go there and with a pencil or something like that, tweak the master bit and then screw up the whole thing and screw up the network. But I would assume that that would get you kicked out of classroom. More questions? Yours? Now you have to put one question up. Can you play text adventures? You can actually, well, you can not only run text adventures.
Just to João, because do not look at me when talking about text adventures, please. I don't want to be related to that.
But you know, the fun thing that they never did, and the system would allow, they were exploring. We fortunately had access from the repository of Álvaro Oliveira, which was one main collector for all. Well, he was manager at Timex at that point, but we got from his estate, we got a huge set of documentation, and some of the discussions regarding the future of TENET are present in that kind of documentation. And they were exploring quite a bit on what to do with the system, how to evolve it. One of the discussions that they were having was on the way in which this could be not peer-to-peer, but this could be way more collaborative, because they would need to mask this master-slave architecture onto some kind of mechanism that would allow genuine collaboration between students. And one of the things which is discussed is really multi-user games and multi-user applications. text adventures that could be ran, for example, by multiple people at the same time. We have something that we need to still get working for our demo, which is, for example, a tic-tac-toe game, which can be easily ported to this, and in which two students can run on the network and each playing their part. This kind of stuff can be developed quite easily using this architecture.
So my question is, the whole system relies on having the floppy drive present for now, or at least for the foreseeable future. So if someone has, like me, a floppy drive and wants to recreate it, I'll need just to build at least 2 boards to make communication, and that will probably work, assuming that someone will also make available the floppies with the actual content.
We have the disks and disk images, so we'll make them available.
Yeah.
So what do you need to do if you want to make this at home? If you look at the board, so let me go a little bit back. If you look at the board here, the board already has 2 components, 2 main components. The board has a set of circuitry that is pretty much the same as the Timex interface. So that connector to the floppy drive, that's included here, plus the network stuff. So this is both at the same time. It's that little box there, plus the network stuff, all in one. So the way in which we do, what we are advising people to do when trying to toy around with Tenet, it's actually to wait a few weeks more. I would say couple, oof, people would kill me. Wait a few weeks more for us to make this available, because this gives you the whole thing. This gives you the same circuitry on the larger board, but instead of having to open or do this very acrylic contraption that we have here, instead of opening your computer, you can just plug it in on the edge connector, and you have both the interface to the disk system and the communication jacks so that you can connect to the network. So with this tiny contraption here, you get the full benefits. If you want to go crazy and try to do stuff yourself, it's tricky to separate the network part from the FDD part because the ROM code is very intertwined. Nonetheless, fun note, you can boot a system using cassette. It's just that most commands that, for example, on the student, if you want to, on the student, write something to the disk drive of the teacher, it won't work because you won't have a disk drive there. But for running this software here, you can load it from cassette, for example.
In case of an exam, for example, and the master sends the questions to the students, the answers of the students could be recorded on the disks.
How would that work? We actually don't have an exam-taking software, which is a pity. And it's rather easy to be produced. How would that work? For an exam, the teacher would send an exam program to the user, to each of the pupils, to each of the students. And that exam program, which can be a very basic program, would fetch the exam questions from the teacher, run the questions through the students, and then gather them and send them in BASIC to a special file, like, for example, student1 answers.whatever, back to the disk drive. And in so, you'd have the controller, the exam controller running on each of the students, taking the answers and then pushing them to the teacher. The teacher would probably have an evaluation program on his desk and would be able to score the exam and get results to the classroom.
We were addressing several things at the same time here. So regarding this question, João was explaining me the changes that were made to TimeWord to record centrally the results. So I think it's easy to accomplish what you were saying. And I wouldn't say it's a limitation, but a thing we have in terms of context that may be challenging for people outside of Portugal for now, is so all of this relies on the FDD existence. So my challenge to you, just to tease you a little bit, is perhaps in the future we can think about somehow emulating or replacing the FDD, or considering the other floppy disk systems that existed. I don't know if they could be used or not. So I don't know if we ever thought about that, but I think that's a challenge for the future. And just my comment.
Let me take a deep breath, because that's a pretty loaded question. Nonetheless, it's obviously a question that's on our minds. So let me take probably a two-step answer to that. One is how to make this available to most people, and how to make this available in such a way that most people can toy around with it and be, well, I would say productive, because we're in 2024, right? But at least toy around with it in a productive way. One is via, once again, going through some kind of design or redesign of this board that we are making available. That's clear, in which more people can get this on their hands. But still, that means that you need to have at least 3 machines to have something that's really fun. Because you need to have a master, you need to have 1 slave, but crap, you have 1 master and 1 slave. So what good is that? So, yeah, sure, but you still need to get 3. Ideally, we had been discussing the way in which could this be used to connect Spectrum users throughout the world via some kind of internet interface? And that's a very common question we're getting, and that's clearly something that people want to see coming out of this. That's one. The second one is, even if we somehow dematerialize this, even if we somehow take it out of these atoms encasing and turn it more into the virtual level, into the bytes concept, how can we do this? Well, there's a very common emulator called Fuse, and Fuse has a mod, has a patch that is well known within the FDD users community, which allows Fuse to emulate an FDD machine. So you can actually write disks, write disk images from Fuse, and then write them to physical media. We need to try to address the fact that with some extra tweaks and some extra changes, this same architecture can run TENET and can virtualize the access to the network. And that's a way forward. Finally, there's another hypothesis which is completely different, which is going through the FPGA domain. Something along the lines of reusing extra capacity on a Mister system or on a Spectrum Next or some along these lines, in which you'd be able to reuse some capacity of their existing FPGAs to emulate stuff. This is, for me, it would be very elegant, because these are platforms that are openly available. Nonetheless, there's a problem, which is capacity. Why? Because if you would want to emulate the whole thing, you would need to emulate at least 3 processors. How come? Let me go back one bit more. You'd need to emulate the Z80. You'd need to emulate the Z80. You'd need to emulate the 8031, which is the communications processor, and then you need to emulate an extra Z80, because on the controller here, the controller is pretty much a computer on its own. So at this point, you might, for some platforms, such as the Mister, this would not be a problem. For other platforms, such as the ZX Spectrum Next, this probably is a problem, because even on the Kickstarter 2 machine, the extra capacity on the FPGA is not that much. Please do. We have an extra question from João.
I'm not such a technical guy as you are. I left that part of my career a few years ago, but I think we are in the right context to throw this, let's say, stupid idea to the table. It may or may not be stupid,
sure.
But so we have Lord Cox is there, so we have Miguel over there.
Yeah.
So we need to find a way to put this interfacing with the DivMMC running in some Spectrum or whatever. So we have the community that gave us the Div IDE, DivMMC. We have the guy that did the XDOS. Is also a volunteer in the museum. Come on, let's find a way. You find a way.
Let's find a way.
I just give the idea.
Let's find a way. Let me take that. Let me take that on 2 notes. The one which is, of course, and now on a more serious note, There's obvious space for having disk images being read from some kind of a div MMC or div IDE device, or some kind of div MMC or div IDE like device. So there's obvious opportunity there, especially if you then couple that with some kind of reimagined hardware. Like I was thinking about the board that powers the Misters, the D10, which is now becoming out of stock, but that's a whole different story. But basically, you could create a tiny box. We could even, now I'll be the one imagining stuff, huh? You can even put it on a reduced version of this. Let's not call it the FDD, but we can go on the same route, and this would allow you to just plug an SD card and take a full FDD-like system that would be able, if we design it from scratch in such a way, to run TENET plus the stuff with 2 tiny jacks on the back. That would be cool.
To add a little bit of incentive to that idea,
Hit me.
we did kind of a similar thing with the Apple old stuff, like the old Macs. They had the local talk network, and a few folks prepared everything for people to build, to join the global talk, as they called it, which was essentially a local talk running over the internet. So there was a very obscure software made by Apple that bridged TCP with local talk. And we did that, I think it was like 1 or 2 years ago. And it was super, super fun. Like we were printing on dot matrix printers that were on different continents and playing games with each other and sharing
Really cool.
files. So it was easier to do because the software was already there.
Sure.
But it was super, super fun. And seeing all this technology that was never meant to run at this scale to actually work without any modification, it was great. So if you can do that, you can be assured that people will have a lot of fun.
I feel energized.
All right.
Thanks.
Thank you.
Just a request. Can you show a client or a student asking or loading a specific game, for example?
Sure. I'll load something which might be on the disk. Let me just check what's on the disk. So, we don't have Chucky Egg on this one, but João Encarnado, welcome the guy. He's our main FDD preservation guy for software. Change the disk. Change the disk, that'd be fun. Yeah. Because he has this special disk with some games, and he has a favorite. But if you look, João used an option which I hadn't yet at this point, which is file enable or file server enable. What's that about? It's starting that loop, that polling loop between all machines in such a way that machines can request stuff. And just come here before. And he actually asked something here, and it's reading from the disk, and I believe this is a game you guys know. But the only way this student was able... yeah, asteroids and Chucky Egg. But the only way these students were able to load the games from the master's disk was because that option was enabled. Otherwise, since actually that program is a basic program and we don't have multitasking in ZX Spectrum, what you have is that there will not be a running polling loop between all of these machines. So any requests from here or there would be ignored up until the moment in which we would enable that specific option. And Rui already has a follow-up one. So let's hit it. Let's go. Thank you, João. That was great.
Can we hit the technical questions?
Please do.
So, how exactly is the interrupt routine that receives the communication from the clients actually handle the communication while we are, for example, playing a game? So it's an interface probably that requires an interrupt.
Being very technical here then, the way the 8031 and the Z80 work is really simple. So you have do remember, yeah, let's kill it. Yeah. So do remember that you have two processors running at the same time. You have the 8051 and you have the Z80. So the 8051, the only thing it's doing right now is exchanging packets with the network or listening, depending on that specific protocol I mentioned with the 8051 multiprocessor thing. So when it gets a package for its own IP, then it takes the package immediately. It takes the package from the network. So asks the master, okay, that's for me. Just give me your stuff. Takes some bytes, puts it in that intermediate RAM, then gets the checksums done so that it's a correct package, and then signals the Z80 via an NMI. That's your answer. Signals the Z80 via an NMI, and the Z80 can then go. There's a flag being set, and the Z80 knows that it's its turn to go to the RAM and get the package from there. And then it signals on an 8051 port, then it signals, I'm done, you do your own thing. So they communicate via that dual port RAM that we have here. Let me just go next here. There we go. So traffic comes from the jacks. It goes through the 8051 via the line drivers. It's running this ROM, and this is just doing networking, right? The moment there's a package for this machine, it gets the package, writes it here, and then via this paging logic sends out an NMI upwards to the other board, to the Z80. The Z80 wakes up, starts running this ROM, gets the contents that were put here towards the main RAM, basically, does whatever it needs to do, and then pages out stating look, I'm done. You carry on doing your own thing. And this happens in an instant. You can actually see, if you push it, you can actually see that you get the normal Z80 software kind of buggy because the context switch is not 100% perfect. Nonetheless, it should. It's mostly timing that makes it not perfect because the code itself guarantees that states are maintained quite isolated.
2K mem, right?
That's a 2K mem.
2K mem. That means that loading programs is done 2K at a time.
Loading programs is done at most 1K at a time, basically, not even.
Okay, cool.
Because that 2K RAM serves two main purposes. One, which is the normal FDD buffer, and then on top of that, you get the TENET buffer.
Okay, finish the board, give me 2, I'll make a game.
I'll hold you to that.
Promise?
There we have one, final one, or even more. As Captain America would say, I can do this all day.
Okay, take the example of Chucky Egg. Disregard that is a game, but taking, for example, that the game is some kind of software or to do some kind of procedure. And the student is having some problem to jump over a hole. Can the master take over the keyboard and do like this and show him in his own computer how to do that?
In Álvaro Oliveira's documentation, there are some exchanges for ideas for the future of TENET. It's slightly hinted that they would consider going that way. It's not explicit, but it's slightly hinted that they were considering it. It's not implemented on these specific systems. But that's a really good idea, of course. I believe we're done, right? Thank you guys so much for, well, spending all this time with me now and with João as well. With both Joãos as well in that regard. And we'll be here for the next minutes, so any questions coming by, okay? If you guys online want to follow up on this somehow, we're more than open for questioning, more than open for discussions, and we kind of love this with heart passion, as you can see. So thank you so much.